Hello everyone. So this is the fifth video of our UART video lecture series, and today I am going to explain the code of baud rate generator. So in this baud rate generator theory I already explained in my previous videos, so you can go through that. In that why we are going for the baud rate generator, we know that because in UART communication protocol we don't have common clock between the master and slave. So in that place we use baud rate, right? So that they can transmit and receive with the same data rate. Baud rate means data rate. So they can transmit and receive the data with some common data rate. So that's why we are going for this baud rate generator. Okay. So I have written this code, baud rate generator code already in this UART tool. So I am going to explain this. First we need to write module name. This is, I have written here baud rate generator, and there are some inputs like input clock, reset, and there is a one output. Output is also clock. Right. So what we are doing here, we are taking input clock from the board. Means what is the internal clock of that board? We are taking as the input, and we are converting into the some uh, clock which we are going to use either in the transmitter or in the receiver side. Okay, so that's about input and output. Now here parameter clock frequency. So here we use 100 megahertz value. Why we are using here 100 megahertz? Because which whatever the board we are using in this UART hardware implementation, that board internal clock frequency is 100 megahertz. So that's why I mention here clock frequency 100 megahertz. Okay. Here we are using baud rate, that is a fixed baud rate, which is 9600. You can use any baud rate, which has already I explained what are the baud rates are available. So you can watch my previous videos. Okay. And next is here I mention one register, counter register. Why we are using this counter, I will explain in the next part. Okay, so that is a 14-bit counter. It's a 13 down 0, so it's a total 14 bit. Then we need to divide this internal clock by baud rate, so that we can divide our internal clock. Because this clock frequency is huge, we need to divide this clock. So that's why we are dividing with baud rate. And this what value we will get after dividing this? It's a 100 megahertz dividing with the 9600. So around 10,400 value we will get after dividing this. Okay, so divisor slash TF, this value around 10,400. Just remember this value. I will explain why we are using this counter of 14 bit. Okay. So next is we need to write always clock. So always at the pod edge of clock means each pod is positive edge of clock. This will execute. Okay. So if reset is there, then clock out. Clock out is 0 and counter is 0. Means both values, output clock and counter set to be 0. Okay. If reset is not there, reset equal to 0, then this condition will check. If reset is not there, and if reset is not there, and counter equal to divisor slash tx minus 1 means this value. Whatever we are calculating here, around 10,400 we are getting. So that is that value equal to counter, then these things will happen. Then what will happen? Clock out TF will toggle. It's a negation of clock out TF, right? So whatever the previous value of clock out TF, that will change to, means that will toggle. and again counter set to be 0. Okay, so what is happening here? Let's counter equal to 0 and this value is around 10,000. So 0 equal to 10,000? No. Okay. Then what is happening? Counter equal to counter plus 1. Means counter will increment. Okay. Then again it will take 1 equal to 10,000? No. Then again counter will increment. It will go up to that value 10,400 minus 1. Up to that value it will go, and if that value, that counter value and this value equal, means this clock out TX will toggle and again counter equal to 0. So what is happening here? This up to 10,000 clock, that clock out TX will remain same. Okay, and after that 10,400 minus 400, around 16 something is coming, at minus 1, at that time that clock out change, means let's take initially clock out TS is 1, then after 10,000 value that will toggle to the 0, and again next 10,000 value it will remain 0, then after 10,000 value then again 1. So that we can easily predict that graph, that with respect to the internal clock frequency, this clock out TX frequency is changing, right? Because it is changing after 10,000 clock pulses. So we can easily say that this clock out TX is different than this internal clock, right? So in this way we can easily understand this code. So this is the code for this baud rate generator. So you can easily explain. And why we use this 13 down 0 counter? After dividing this clock frequency with the baud rate, we are getting around 10,000 values, right? And if we can calculate this 2 to the power 14, these are the 14 bits, right? So if you calculate 2014 or 2 to the power 14, then what value we will get? Around 16,000 we will get. Uh, and if we will use 12 down 0, means 13 bit counter, then 2 to the power 13 means around 8,000. So 8,000 is less than this 10,000, right? So we can't use here that 12 down 0, means counter 13 bit counter we can't use because that value is less than this 10,000. So that's why we use here 14 bit counter, so that we can easily go to up to this value. So that's why we use this 14 bit counter. Okay. So this is all about this baud rate generator. If you like this explanation, just like this video. Next in upcoming parts, I will try to demonstrate on hardware. Okay. Till that, thank you.